Hi there, you're in the lab with your mate JJ. Today is Learning the Art of Electronics Day. Today we're learning the art of electronics. My silly job title for today is the plugger-innerer. I'm the plugger-innerer. Of course, in Learning the Art of Electronics videos, we go through our epic tome, Learning the Art of Electronics. It's a hands-on electronics lab. We're working our way through the book, and today we're going to finish the first chapter, which is 1N DC circuits. So the N stands for notes. So this is the notes for the DC circuits part of the course, which we're just getting started with. Of course, we're learning mostly about voltage dividers and the Fig-1N model of a circuit. So today, in the theory part of the course, we will complete the DC notes chapter, which is good. So we'll get to the end of that chapter. We will be reviewing the whole chapter at the end of this video. But before we do the theory and notes revision, we're going to pop over to the bench and do a little prac. This is something that we actually covered earlier, but that I found myself confused about, that I want to revisit with you. So we'll be jumping over to the bench. I'll show you what the confusion was, and we'll do a simple, just a very simple experiment to prove the Kirchhoff voltage law, which regards the sum of voltage drops around a closed loop of a circuit. So that's what we're doing today. We're going to have a look at Kirchhoff's voltage law on the bench, and then we're going to go through the notes on the computer together, and that will be the end of the notes for this chapter. So we'll be able to start the next part of the course, which is actually the lab for DC circuits. That's what we'll be picking up next week. So let's pop over to the bench and have a look at the Kirchhoff's voltage law. All right. Well, here we are on the bench. Now, I'll just show you what we'll be doing today. I have to flip through the book for a bit. So, there was a picture here. This is Kirchhoff's two laws, and on the left is KVL, which is the Kirchhoff voltage law. Now, I'm sorry if I'm not pronouncing Kirchhoff correctly. I'm not sure exactly how to pronounce it. And this is the diagram that was given to explain this law. And when I saw this, I thought it was saying that each of the boxes, A, B, C, or D, was like a power supply, like a battery, say. I thought each one was a battery. And I thought if you took all of those batteries and you connected them all up like that, you just have a massive short circuit. So, I mean, you would have very minor resistances on the wires, and then you'd have all this power source, and it'd just try and draw infinite current, and it wouldn't, of course, but it would certainly make your batteries unhappy. So this was a misunderstanding. These circuit elements aren't necessarily power sources. That A could be a battery, and then B, C, D, and E could be load, could be resistors. And by the time you get all the way around to here, the sum of the voltage drops across all of those will add to 0. So what we're going to do today, and I was getting prepared to do the experiment with these things and put 5 power supplies in series like this, and I thought no, it can't be right, and it isn't right. So what we're going to do today is we're going to make a 3-element circuit. We'll have A will be the power supply, and then B and C will be resistors. We'll make them like 1K and 2K, for instance, or we might even just make it 5K and 5K, so they're the same. We'll think about it, or we might even do a few different cases. Yeah, we will. We'll do a few different ones. So let me just put the book out of the way. And here is our notebook. So the date today is the 28th of October 2025. I'm Australian, so I put the day first. This is learning the art of electronics. And this is Fig-1N.6. So Fig-1N.6. All right, and we're going to have, let's just say, so we're going to have resistors A and B and a power supply, and we'll feed in, what do we feed in? 10 volts? 10 volts? Sure. 10 volts, and then we'll we'll have to pick some resistors. So here is one resistor, and here is another resistor. Now I might as well just show you quickly. Just give me 1 sec. All right, so that's my my power supply at the back here. I'm actually going to set it at 3 volts, so I'll set the voltage at 3, and and the current over current. We'll just put it at 1 amp. So it's in constant voltage mode, which is good. Now we're going to run the positive. I'll just flip you over to, oh, well, now you can see there. So we're going to take the red line out and run him in here. And then we'll run this over here. And we just need one in the middle there, going from there to there. Now the power's off at the moment. Let me throw you back over here. So what we're looking at is the first and then the second resistor. Now they're all switched off. So these are at 0 at the moment. So we don't want to turn anything on while there's no load. And we're not going to use 10 volts. We're going to use 3 volts. And we're going to have let's have some points, and we'll just label this point A, and this point B, and this point C. And for various, we're going to have, it's always going to be 3 volts. So we'll have a value for A and a value for B. And then we're going to have the voltage between A and B, the voltage between A and C. Actually, we might do that. We might do the voltage. We'll do the voltage between A and C first, and that should always be 3 volts. And then we'll do the voltage between A and B, and then we'll do the voltage between B and C. And we're only interested in the current, the voltage law, so we don't need to concern ourselves with currents in this experiment. So okay, so let's say that we've got 1K on A and 2K on B. So that'll be 1K on A and 2K on B. Okay, and we're sending in 3 volts. Now we're going to need our good old multimeter here to do some measurements. So let's put our jumpers in, and we'll put this on DC voltage mode. That looks good to me. Can you see that? We put that there. Can you read it? Yes, you can. Very good. All right. So just confirming, this is oh, they're not that. Okay, this is on 1K, and this is on 2K. Okay, so A is 1K and B is 2K. So, what's the other thing we could do? We could measure. We could measure current. I wonder if we just if we use this, if it'd give us a current reading. Let's put it on. I don't know what to expect. Let's try putting that on there and just see if we get a reading or not. So here we go. On with the power. Okay. So it's delivering 3 volts. And it's drawing not very much current at all. It's negligible amount of current draw. Is the circuit complete? I think it is. So let's check the voltage across the two. So it should be there. Okay, and that is 2.996. 2.996. And now we want to do the voltage between A and B. So let's just pop that there. And that is 1.002. 002. And then we want the voltage between B and C. And that's 1.994. All right. So what we should see is that AB and BC will, if we subtract them from the total voltage, it'll be 0. So does that make sense? Oh, look, the current draw is so small that the current meter is not getting a reading. I'll just I'll turn it off for a second. Let's be brave and let's knock it back from 1K to 100 and from 2K to 200, and let's put that in there. All right. Now let's see what happens if we turn that on. All right, now it's drawing, it is actually drawing a little bit of current. You can't see it on here though. Oh, there we go. Yeah, okay, that's pretty good. So the up the back here on the power supply, it says it's drawing 8 milliamps, whereas this current meter here is picking up 0.02, which is about 20 milliamps. So who knows which one's correct. Let's get a third reading. Just give me a second. I'll get another multimeter in the picture. Here's my old Fluke. Let's throw you back over here. This is the Fluke. I'm just going to set it up as a ammeter. So we want that in there and that in there. And let's just let's take this out here, and let's put that there. So let's put this in milliamps, and pop him in there. All right. Oh, okay, and the polarity is the wrong way around. All right, there we go. So, what can we say? All right, well, this is quite a bit off, but it's not surprising. That's a pretty dodgy way to measure the current. It says 0.03, so it's reading about 20 milliohms on this meter, but it's measuring 8 milliamps here and 9.8 milliamps here. I reckon the flick will be giving us the best reading here. So, okay, that's all well and good. Let's do the voltage measurements again. So let's disconnect this and let's put this back together. Now, and we'll get rid of this. We're not interested in current anymore. So this one, we want to do first of all between A and C. And that's giving us 3.00, 3.007, and then AB is, oh, is that? Yeah, interesting. 2.866. And then we want BC. Uh, 0.141. Well, I certainly wasn't expecting that. Ah, of course. Look, I've got this 10K here. That's why those readings came out so wrong. I was looking at these numbers and that's not right. So let's cross him out and let's just turn him off, and we'll put that 10K out. So it's 100 ohms and 200 ohms. So let's start again, 100 and 200. Now the voltage VAC should just be the 3 volts. So what are we getting there? 2.999. 2.999. And then AB is 0.508. And then BC is 2.490. And again, if we just crunch the numbers, where's my calculator? Hang on a sec, I'll find my calculator, I'll be back. All right, I'm back and I got my calculator, and just what I want to show is that if we take the voltage across the whole circuit, which is 2.999, and then we subtract 0.508, and then we subtract 2.49 equals 0.001, which rounds off to 0. So and again for the 1K resistors, we can have 2.996 minus 1.002 minus 1.994 equals exactly 0. So that just shows you that you drop, by the time you get around to this point in the circuit, you'll have dropped all of the voltage. So all of the voltage available here is 3 volts. You come across here and across here, it'll be 0. And of course, the voltages A, B, and B, C are in proportion to the resistances. And here we used 3 volts, and then we used 3 parts. So one part is 1K here, and one part is 100 here. So I suppose we could just do, let's just do one more just for the sake of completeness. We'll do something that's a bit different. So we'll do, say, 500 and 500. So again, the voltage across the two resistors should be, okay, 2.998, and then we want the voltage across AB, which is oh no, we've got to change the let's turn him off, and we'll put him in, so we want well, we were going to do, let's just do 400 and 400. So that's 2 400s. Turn him on, and we'll just confirm that this is still the same. So it's 2.997, which is close enough to 998. And then we'll check the voltage across here. It's 1.09. I wasn't expecting 1.09. Have I made a mistake again? I'm not seeing a mistake. I was expecting that to be half, but it doesn't seem to be. Anyway, let's write it down, 1.090, and then from here to here, 1.906. It's not making sense. 1.906. There must be something wrong. I'm just gonna take a break while I think about this. All right, I'm back. I was going to resort to measuring the resistors. I think I just knocked this one here. You see that 300 was accidentally knocked, and when I put him back, I got the right reading. So let's just fix up this line, and let's do what we actually did. So we made it 400 and 400. And let's again just measure the total voltage across the whole circuit. So it's 2.996. And then the voltage across AB should be 1.5 or thereabouts. 1.499, 1.499. And then the voltage across those two ought to be 1.5 as well, which is 1.497. And so using the old calculator, we'll go 2.996 minus 1.499 minus 1.497 equals 0. Exactly right. Cool. All right, so that concludes the prac for today. I just wanted to demo Kirchhoff's voltage law and get past the confusion of it being all voltage supplies. It's actually load as well. So let's go over to the computer now, and we'll go through the notes for this course. All right. So here we are on the computer. I'm going to just jump over to the website, the ITL wiki, which is of course the wiki for the show. just loading there now. Yes, so this is in the lab with jj.com/wiki. And we've got a number of projects here, but we're doing Learning the Art of Electronics today. This is the notes for Learning the Art of Electronics. Let's load that up. So I've moved the notes over to its own page, so we'll just open that up. Now this is going to be completed today. This is the last time we'll be going through these notes. So some of it's revision. There is some new material here. So actually, you know, I might even just take you back. Yeah, here. Let's edit this together just quickly. Now, I'm sorry I didn't get a video out last week. I was actually crook. I was vomiting. It was awful. So, okay. This is October. Today is the 28th. All right, and we're still working on 1N DC circuits. And I'm going to say today, we were doing the Kirchhoff's current law. So let's just I'm just looking for the here it is. There we go. So it's Fig-1N.6. And the reading for today was, let me just have a quick look in the book here. Page 24 we're up to. So that's 24. And I will fill in these details after we've done our video, which we're recording now. So as you can see, we're doing Fig-1N.6, which is like from way earlier. But I went back to it just because I was confused about it. So let's take you to the top, and we're just going to read through this whole page. As I said, 1N DC circuits, we're going to complete that today. So this is the last time through these notes. Some of it will be revision, but there's some new material at the end. So the main thing that this chapter is about is voltage dividers. That's a big part of what we learn in this chapter. In the course, of course, in the whole course, the laws, rule of thumb, and tricks that constitute the art of electronics. So that's what we're learning about in this course. When delivering power to something, the something is called a load. This course is concerned with using electronics to model and process information. So it's really our goal to power things, but we do, of course, do that from time to time. They ask the question, is it better to model information with voltage or current? And the answer is it's better to model information with voltage, because when you model things with current, you need to consume power, whereas when you model things with voltage, you don't necessarily need to consume power, or at least not very much power. So Ohm's law, very important, V equals IR, where V is for voltage in volts, I is for current in amperes or amps, and R is for resistance in ohms. And as they say, a volt is what pushes an amp through an ohm. You can also say 1 volt is the work done
as one adds 1 joule of potential energy to 1 coulomb of charge. Ohm's law is useful, but it only applies to resistors. So there are plenty of things that aren't resistors and they behave differently. The inverse of resistance is conductance, and conductance is measured in Siemens. So you can say G equals 1 on R, where G is conductance in Siemens and R is resistance in ohms. Generally, in most metal conductors, conductivity degrades, which increases resistance when temperature increases. So thermal activity excites the metals and they jump around, which means there's more friction and collisions happening in there, which causes resistance. So that's not a hard rule, but it's a usual rule. This equation here is the energy, the electric field that arises between 2 points with a voltage between them at this distance. That looks a bit physicsy. We don't do too much physicsy stuff in this course. There are various strategies for making a resistor. There's carbon composition, there's carbon film, there's metal film, and there's wire wound. And they make the note again that many electronic components do not obey Ohm's law. So don't expect to use Ohm's law where it doesn't fit. It only works for resistors. We can extend the reach of Ohm's law with dynamic resistance. So dynamic resistance can be computed by the change in voltage divided by the change in current. So we can talk about the effective resistance of devices. And there's some examples here. So you got a resistor, for instance, just a straight line. The lamp changes its resistance depending on the temperature of the filament. And the diode just tapers off like this. And a current source is a straight line. That's an ideal current source. And of course, there's no such thing. But that's what an ideal current source would look like. And we looking on this side of the graph here, the tangent to the diode curve gives us 150 ohms at 0.2 milliamps. So this is the details of the diode curve from over here, which looks like that. So at this point, you can compute the compute the dynamic resistance. So something which isn't actually a resistor, at a specific point, you can still compute a dynamic resistance, which is like an effective resistance. And this curve was plotting V against I. Usually it's an IV curve where I is on the y-axis and V is on the x-axis. But the reason they flipped the axes here was so that this result comes out in ohms. If you've got the typical IV curve, the tangent will come out in Siemens, which is conductance. So that's why they flip the axes here, so that this number would be ohms. Now we're going on to learn about power. So power is the rate of doing work. Components will have power ratings, which and usually components with higher ratings will be physically bigger. So, and he says here, copper traces on a circuit board can help a little with dissipating heat for SMD resistors. So, formula for power in watts, P equals IV, and then substituting Ohm's law, you can get P equals I squared R and P equals V squared on R. And then to find the minimum resistance for a quarter resistor at 15 volts, you just express it like quarter watt equals 15 squared on R min, and then you can solve for R min and you get about 900 ohms, which is pretty close to 1 kilo ohm as being the minimum safe value at 15 volts. Current, speaking of that, I'll just check that I'll just go and turn off the power supply from the experiments we were doing earlier. All right, so current measures charge over time, voltage measures work over charge. So when you multiply those together, the charges cancel and you get power equals work over time. And in this course, we rarely worry about power. So mostly we're interested in voltages as signals. Now here's of course the Kirchhoff's laws for voltage and current. The one on the left here is the one that we just investigated over in on the bench. So and there's a similar law for current. Means the algebraic sum of all of the currents into and out of a point is equal. So equals 0. Sorry. So everything that goes in also goes out, and it adds to 0. So here's Kirchhoff's laws. Kirchhoff's voltage law says the sum of the voltages around a loop is 0, and Kirchhoff's current law says the sum of currents in and out of a node is 0. And then you can see the applications of these laws. So series current, the total current is I1 and I2. They're all the same. Parallel current, the total is the current from the left and the current from the right. And then it's the other way around for voltage. So the total voltage for series voltage is voltage 1 plus voltage 2, whereas the parallel voltage is the same. So there's a picture depicting those values. So this is series and this is series and this is parallel. So in this here I1 and I2 are the same, and V1 plus V2 is additive. And then here V1 and V2 is the same, and is equals 0. And the current through here and the current through here adds. You need to know that this is actually a circuit. So it doesn't look like a circuit because it's not all tied off, but it's equivalent to this, where it's all tied off together back here. So we call it a circuit because of this, but we draw it like this. With parallel resistors, the conductances add. So the resistances don't add, but the reciprocal of the resistances do add. So you've got the total conductance equals conductance 1 plus conductance 2, which is the same as 1 on R1 plus 1 on R2. And you can solve that for a two resistor network, and it's R1 times R2 divided by R1 plus R2. And here's some easy cases. So with R equal, you get R times R divided by R plus R, which gives you half R, or approximately 0.5 R. If you've got R here and 10 R here, then you have 10 on 11 R, which is 0.91 R, which is actually less than this. So it's actually smaller than the smallest resistance. And for this one, R and 2R, we've got 2/3 R, which equals 2/3 R, 0.67 of R. So there you go. Now this is handy to keep in mind. When you've got parallel resistances, the small R dominates, and when you've got series resistances, the large R dominates. So over here, the one that matters is the small one. Over here, the one that matters is the big one. And then again, that's just here in a parallel circuit, a resistor much smaller than other dominates, and in a series, the larger resistor dominates. And there's a note here about using a potentiometer as a variable resistor. A potentiometer is a 3-terminal device, and a variable resistor is a 2-terminal device. And the way to convert a potentiometer into a variable resistor is to tie one end of the pot to the wiper, which means if the wiper comes loose, the maximum resistance is seen instead of an open circuit. And this can be important as you probably haven't tested your circuit with an open circuit resistance from this component. So it's just for when the wiper gets old or rattles around a bit, it's better to see the maximum resistance than to see an open circuit. That's why you should get in the habit of tying off one end of your potentiometer when you just need a variable resistor. Now we're starting to crunch some numbers about the old voltage divider here. So we've got 10K here and 10K here, which means that if we put 30 volts in, we're going to get 15 volts out because it's proportional to these two resistors, which are the same, which means that it's a 50% of the input. And again, more and more about the voltage divider, and we go through the different ways that you could calculate the resulting V out. So there's a couple of ways that are presented, and we end up with this. The output of a voltage divider is the voltage in times R2 divided by R1 plus R2. And they encourage you to say to yourself in words how the divider works, so you get an intuitive understanding of how it works. So you might say, since the currents in top and bottom are equal, the voltage drops proportional to the resistances. So in this case, where the lower resistance makes up half the resistance, it will show half the total voltage. So there you go. Loading and output impedance. So we're talking about load now, where we come along and we attach a load to our voltage divider. This is the divider and this is the load. So the first way that we talk about all right, so they're basically showing you that that this and this can be computed as 10K in parallel with 10K, which is effectively 5K. But instead of doing it like this every time, we can use the Fig-1N model instead. And in the Fig-1N model, the load is not part of the model. And we have a Fig-1N voltage, which is the open circuit voltage with no load attached. And the Fig-1N resistance, in this case, is just R1 and R2. And what you need to do is take these as parallel, looking back into the circuit from this point here. So the Fig-1N voltage is just the open circuit voltage with no load attached. And the Fig-1N resistance can be formulated as the quotient of the Fig-1N voltage and the short circuit current. But you know, don't actually short the current. So the Fig-1N resistance, this is the shortcut calculation of Rthev, and you take these two resistances in parallel, R1 and R2, and that gives you Rthev, and the Fig-1N voltage is Vn times R2 on R1 plus R2. So we learn a general definition and procedure for determining the impedance at a point, and the way to do it is apply a delta V, a change in voltage, and measure the change in current, and then the quotient of those values is the impedance. So that's the same as the dynamic resistance, which we discussed earlier. It's going to take a quick break. All right, I'm back. So in this experiment, which we did already, we added the extra volt here. So we took this and we put it in 11 volts, and it affected things. And the extra current comes from the new power source. So rationalizing Thevenin's result, parallel R's. Any non-ideal voltage source droops when loaded. How much it droops depends on its output impedance. The Thevenin equivalent model with its Thevenin resistance describes this property neatly in a single number. So the Thevenin resistance is the output impedance. They're the same thing. And here it is there. Rthev is the output impedance, which is the single number that tells you how much a power supply will droop when a load's attached. Now I asked ChatGPT here, are output impedance and Thevenin resistance the same thing? And it says, yes, in practice, they're the same concept. And then it goes on to discuss that in greater depth. But the one line takeaway is that the output impedance equals the Thevenin impedance. And when you're only dealing with DC or resistive cases, the Thevenin resistance is the same as the output impedance. And I also asked ChatGPT, please explain the Thevenin model to me, particularly why we can treat the various resistances parallel to each other. And I do remember reading this and it was kind of helpful. So Thevenin's theorem, quick, intuitive plus mathematical explanation. Short version. Any linear circuit seen from two terminals can be replaced by a single ideal voltage source, the open circuit voltage, which is the Thevenin voltage, in series with a single resistance, which is the Thevenin resistance. You get the Thevenin voltage by finding the open circuit voltage between the terminals, and you get the Thevenin resistance by turning off independent sources and finding the equivalent resistance seen from the two terminals. So basically you take all independent sources and you remove them and you short the terminals. And then that creates parallel resistances, which you can solve for. I asked ChatGPT as well, please tell me what is a linear circuit and what are other types of circuit. So it explained that the linear circuit has homogeneity, which is scaling, and additivity, which has to do with superposition. I'm still getting my head around superposition. But anyway, these are technical definitions for what a linear circuit is. There are other types of circuits, nonlinear circuits, time invariant versus time varying, lumped versus distributed, passive versus active, analog versus digital, switched, power or switching mode, circuits, reciprocal versus non-reciprocal, bilateral and unilateral. All of this is beyond the scope of what we're trying to learn here. It's just extra if you're interested. And I asked ChatGPT, in electronics, please explain dependent sources in the network. So it turns out that there are various dependent sources which you do not just turn off when you're doing the Thevenin modeling. Now we haven't been asked to take this on yet, but it is interesting and it's here. And they give you the abbreviation for SPICE, E, G, F, and H. And you can have voltage controlled voltage source, voltage controlled current source, current controlled current source, and current controlled voltage source. So there's 4 combinations of what the output is and what the controlling quantity is. And then this goes into some detail about how all of those work together if you're interested, but this is beyond the scope of the book that we're working through at the moment. So so again, we just go through the process of applying the Thevenin model. We take this and we reduce it to this. And we find the droop is the same. There you go. So the note here is, suppose that we try to measure the output voltage at the output of each divider. If we measure with a perfect voltmeter, the answer would always be 10 volts. And then it says here, is it 10.000 volts or 10.0 volts? And the answer is it could be 10.0 volts, but it could equally be a bit less than 9.9 volts or a bit more than 10.1 volts. If the 20 volt source were good to 1% and we use 1% resistors, but we should not expect perfection. And here we've got we've got a set of dividers that have the same Thevenin voltage, but they have different output impedance or different Thevenin resistance. If we perform the measurement, we see the effect of loading by the Rn of our imperfect lab voltmeter. So the first thing that we do is we use the old analog VOM, the volt ohm milliammeter, and we pump in some values. We put in 1K, 10K, and 100K, and we measure the Thevenin voltage, which is just the output of the voltage divider. So this is our voltmeter over here, which has Rn VOM, which is the input impedance of the voltmeter itself. And when we're only measuring 1K, the voltage, the Thevenin voltage, is 9.95, which is pretty good. And then 10K, it's 9.76, which is still a little bit loaded, but not too much. But when we go up to 100K on the analogs meter, the loading becomes obvious. It's 8.05. So the meter shows us 8 parts in 10 across the dividers R Thev, call it R out. We must be dropping the other 2 parts in 10. The relative sizes of the 2 resistances are in proportion to the voltage drops, 8 to 2, which is 4 to 1, which means that the input impedance of the voltmeter is 4 times the Thevenin resistance, which is 200K. And actually, you should be able to find a specification on your analog VOM that tells you something like this. And the one we used was indeed 20,000 ohms per volt. And at 10 volts, that's 200K, which is exactly what we should expect. This is a drawing of the innards of an analog meter, which is actually a current sensor. This is current that moves the meter here. Whereas the digital meter is, oops, I've just clicked, there we go. Okay, we're back. Sorry about that. Yeah, so I was just telling you about this one, which is, this is the digital meter, and it's a voltage detector. So the analog meter is a current sensor, and then the digital meter is a voltage sensor. So the VOM specification for 20 kilo ohms per volt describes the sensitivity of the meter movement, which is this bit, which is the guts of the instrument. And so we're going to do the experiment that we did with the VOM with our DVM. So the VOM was the analog meter, the DVM is the digital meter, and we're going to use larger values. So we're going to use 100K, 1 meg, and 10 meg. Now, when we do 100K, the measured V out is 9.92, which is within tolerance. At 1 meg, it's 9.55, where the loading's becoming apparent, but it's still fairly close. And then at 10 meg, it tanks all the way down to 6.69, where the loading is obvious. So the Thevenin resistance is 5 meg. We're dropping 6.69 volts out of 10 across the Rn of the DVM, which is approximately 2/3. And 10 volt minus 6.69 equals 3.31 volts across R Thev, which is approximately 1/3. So we can compute that the DVM must be 2 times R Thev, which is 10 meg. And here is the results from our this is the results from our experiment. These are the values that we put in. V out is the measurement that we took, and then all these other values are actually just computed values. So we put in this that we did the experiment with 100K. We measured 9.93 V out. The Thevenin voltage is 10 volts. The Thevenin resistance is 50K. The Thevenin voltage minus the output voltage is 0.07. So the computed Rin is 7.09 megs for this, 9.91 megs for this, and 10.1 megs for this. Now, I'm not quite sure why this one was so low, but basically it should be 10 meg in all cases. And if you look that up in the user manual for the multimeter that I was using, you will see it's spec'd at 10 meg input impedance. So there you go. Now I asked ChatGPT, if output impedance measures how stiff or droopy an output is a higher output impedance more droopy or more stiff? And the answer is more droopy. So you want low output impedance and high input impedance. And it runs you through the numbers for that here. And then I asked it to please explain a meter movement to me. I still find it a bit counterintuitive to use the word movement as a noun, but that's what it is. So there's comes with some mathematics as well, and it just explains how that all works. Feel free to check it out if you want to do a bit of a deep dive into analog meters. So what can we conclude about the VOM versus the DVM? The answer is that a DVM is a better voltmeter, at least insofar as its input resistance is concerned. As a current meter, the DVM fares no better than the voltmeter, the analog meter. So then I asked ChatGPT, is it generally better to have low output impedance and high input impedance? And we should already know this, but it never hurts to confirm. So yes, for voltage mode signals, you usually want a low output impedance, which is the source, and a high input impedance, which is the load. Cool. And then there's a digression on ground. So we learn about local ground, earth ground, and signal ground. Sometimes, but not always, local ground, earth ground, or single ground are connected to each other. There are schematic symbols to represent earth, local earth, and signal ground, but they are not used consistently. And sometimes chassis ground is connected to a local ground, and sometimes to an earth ground, and sometimes to both. So you might see this as a local ground, you might see this as an earth ground, you might see this as a signal ground, and you might see any of these as a chassis ground. So it's all a bit of a mess. Here is a rule of thumb for relating the output impedance of A with the input impedance of B. And the answer is that the output impedance of A should be less than 1/10 the input impedance in B. So that's here. This is our design rule of thumb. When the circuit A drives circuit B, let R out for A be less than or equal to 1/10 of R in for B. So it's just a rule of thumb. And we do an example here. We've got a 10K here and 10K here. So what is the Thevenin resistance for less than or equal to 10% droop? And therefore, what R's should we use? So the rule of thumb is that the output impedance is less than 1/10 the input impedance. In this case, the input impedance is 10K plus 10K seen in series, which is 20K. Then the output is 1/10 of 20K, which is 2K. And as R out equals R in parallel with R, we've got which equals R on 2. R on 2 equals 2000, which means that R equals 4K. So each resistor in the divider over here should be 4K, giving an output impedance of 2 kilo ohms. And again, we just look at stacking circuit fragments together. So the idea is that in order to figure out B, you can just ignore A, and similarly you can figure out B and ignore C. So and then I just run through the numbers for this here, but basically here it's 20K, and then with C attached it's 18K. So C affects B, but not by more than 10%. And now there's two important I'm going to need to fix that. There are two important caveats or exceptions to our rule of thumb. And one is that when you're using signals that are currents, and the other one is transmission lines. So the rule of 1N.6 for relating impedances, that's our 10% rule, is useful and important, but we should note two important caveats in which it does not imply. Signal sources that provide current signals rather than voltage signals. At the moment, this distinction may be puzzling, but it's an important difference, which we'll learn more about. And high frequency circuits, where the signal paths must be treated as transmission lines. So there's a whole appendix C on transmission lines. I'll try and get the notes written up for that at some point. It's not done yet. But basically for this course, we don't worry about currents as signals, and we're not likely to encounter transmission line problems at the frequencies that we'll be using. But eventually you will need to learn about such things. So, and then we just finish up with some stuff for ChatGPT. I have found ChatGPT really helpful in the absence of a tutor. I asked the question, for a voltage divider made from two 10K resistors, what is the input impedance of the circuit? And explained to me that's two 10Ks in series, which is what I suspected, but it's good to have that confirmed. So that was good to learn. And I asked it, if you're going to connect circuit A to circuit B, and circuit B has an input impedance of 20K, what output impedance for circuit A will result in 10% or less droop? And it helped me come up with this. The answer is 2.22 kilo ohms or less. And it says the rule of thumb for less than 10% droop is to make R in greater than or equal to 9 times R out. Whereas the 10 times rule is what we use, which is a bit more conservative and yields 9.1% droop. And then I asked it to please explain how you derive the first equation for droop, which is this one here. First in terms of voltages and then in terms of resistances. And it explains here how it did that. So it figured out loaded in terms of source and resistances, and then it substituted in here the values for VS, and then that cancelled and simplified, and you get down to this expression, which is purely in terms of resistances. And that's everything. Then the final part of this book is recommended reading. So the reading in the textbook is chapter 1, particularly 1.1, 1.2, and 1.3. The appendix C for resistor types, and the appendix H for transmission lines and impedance matching. So that concludes this chapter. So that's the end of the notes. It's the end of the chapter. In the next video, we'll be doing a different chapter, starting a new Wikipedia page. So I'll throw you over the farewell cam and we'll wrap up.
And that's a wrap. So we made it to the end of the first chapter of the book. Great. So next week we'll keep on keeping on. We'll be looking at our first lab, so I'm looking forward to doing that. We've been working through the notes of our DC circuits. We're learning about voltage dividers, and we're learning about parallel resistances, and we're learning about Fig-1N model. We've also learned about the Kirchhoff's laws, current law and voltage law. So we've made some notes about current signals and transmission lines. So yeah, we've learned a number of things already. So yeah, next week will be the first lab, so looking forward to that. And that concludes this video. So I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.